So our next speaker comes to us from the University of Washington. He's a general internist. He was a history and English major as an undergrad and has no business talking about any of this stuff. So we'll see how that goes. So I'm talking about phenotypes today, and it should be, I think, much less math than the last talk, which was really quite good. I thought that was an excellent introduction that will take you all through to the GWAS tomorrow. And in the exercise tomorrow, there is a particular phenotype that's there. And I think it's memory is what we finally put on there, that you'll be doing a GWAS of from the ADNI data set. And with Shannon's talk earlier, you saw a really nice intro to the vast array of phenotypic data that ADNI has collected. And it's $100 million worth of investment plus on those data from that highly selected population of people. And there's extensive genetic data, which we'll be dipping our toes into tomorrow, but there's a lot more capacity for that. So my goals today for this talk are really to talk about phenotypes kind of in general, and to maybe push our understanding a little bit in different directions. So my ding, do I have to be closer? Push the other way? I'm going backwards. Okay. Nice. History and English, not tech major, right? So I'm going to start with the case control Alzheimer's disease phenotype, which I think is really important, and then we're going to move beyond it. So my conclusion for this talk at the end is it's the phenotype. I think it's really a critical thing for this group of people to understand how important your expertise is for the future of genetic research on Alzheimer's disease, is that there's so many important things to do with the phenotypes. And there's a lot of genetic expertise in the world and a lot of it in this room who will be very happy to collaborate with content experts. And it's really key to understand and have great phenotypes. And it's very important for the genetic productivity in the coming decades. Will be additional understanding of and analyses of good phenotypes. And just some freebies here, other aphorisms. And there's not a ton of aphorisms in my lab, but the other ones are, there is no such thing as a small grant. Every grant is important to be cherished, striven for, etc. And then the third one is look at your data and look at your data labels, very key. So those are the three ones that we have. But the first one is, it's the phenotype, stupid. So the AD case control. So wouldn't it be lovely to have drugs where we could either prevent or treat Alzheimer's disease? So we're going to take a whole bunch of people with Alzheimer's disease and see if there's any differences between those people and people who don't have Alzheimer's disease. We'll identify some genetic characteristics. We'll follow through on those. We'll get some druggable targets, and we'll cure Alzheimer's disease. That's really the GWAS story in a nutshell for the case control phenotype. And you've seen this paper. This is the IGAP paper from 2013. And this is a picture of the authors, several of whom are in this room. I think I'm on the fifth or eighth line. I've forgotten. And you've seen this Manhattan plot. And things that haven't been said about this, the ones that are in black font had previously been known. The ones that are in red font were newly discovered as of the IGAP paper, so the Lambert paper. And you now know this negative log to the base 10 of p, where that comes from. You know this is 5 times 10 to the negative 8th, which is 0.05 divided by 1,000,000. So you've already learned a ton today. You know that each and every one of these labels is wrong, wrong, wrong. And I think this is really interesting. So we had tons of power to find common variants at presenilin 2 and for presenilin 1 and for APP. They're not there. These are the previously identified loci that were in the black font. These are the new loci from this discovery sample. Important to recognize that, and we've talked a little bit about replication and the importance of replication. This was a signal that looked like it was there from a pretty rare SNP. So this was in 1.7% of the population and a fairly big effect size, because otherwise you couldn't have seen it. So this is 27% protection for that SNP. It wasn't confirmed in the replication sample and is sort of dropped out of the list. This happens. It's a known thing. No one did anything wrong with DSG2. They're reporting what they see. Not everything gets replicated. And as we get more and more confusing, difficult phenotypes, it's harder and harder to replicate. And replication is absolutely critical to know, is this a real thing or is this capitalizing on chance? The initial GWAS excitement, the papers that were coming out were so like, oh my gosh, I found this thing with a p-value of 0.0001. It's great. And nothing replicated at that level. So we talked a little bit, I had forgotten who was saying, it may not be a great idea to lift a lighter rock, right, to meet some easier threshold. And it's a tough battle, but it's the case that even with a really conservative 5 times 10 to the negative 8 threshold for a p-value, not everything replicates. And then in the combined analysis, so these are more sort of discovery with all 74,000 people in this big meta-analysis, and Joey always corrects me, it's 74,046 people. My bad.
And those people don't all have GWAS data.
Yeah.
Everyone who knows the data set.
Right. So with the combined group, these ones made it to genome-wide significance, and they're included here. I think this is really interesting. So this is a minor allele frequency for the 20 IGAP SNPs. So there's only one at the 0 to 5% range. And Allison showed that great graph from Terry Manolio's paper that shows the frequency of variance and the effect size, and sort of thinking about, hey, APOE is a fairly common SNP with a fairly big effect size. That's unusual. In all of human diseases, that's unusual. And it's lucky because we have this control that's spiked in. If you're doing an analysis related to Alzheimer's disease and you don't discover APOE, there may well be something wrong, right? Most diseases don't have that. We're very lucky in Alzheimer's disease that we've got this sort of positive genomic control. So there's only the one that's as rare as 5%. And mostly what we find here is common SNPs, where the median minor allele frequency was 31%. So very non-Mendelian. This is not a childhood disease. There's no way this is something that's going to be related to a population selection pressure. So it's a little bit different than most of what I have thought of about genetics before I did Alzheimer's genetics. So I think that's interesting. And I think the other issue here is just absolutely power. At 74,000 people, we're still underpowered to find even medium-sized effects for rare SNPs. And there's an awful lot more rare SNPs than there are common SNPs. So when we impute more things, it's the rarer stuff that we're going to be seeing. Here what I've done is I've taken those same IGAP SNPs and I've sorted them. I've flipped a bunch of them so that if it was a protective SNP, I flipped it and it's got an asterisk. So the SLC24A4 RIN3 SNP was protective, and I flipped it over here so it's 1.10. And the way you know which ones are SNP'd is they have an asterisk. And I've sorted these, as you can see, by the odds ratios. And this is the middle of that distribution, the interquartile range, more or less. Don't quote me on 25th percentile and where that should be exactly. Anyway, so the 25th the interquartile range is from 1.08 to 1.16. So a point was made about how much of height do we explain? How much of Alzheimer's disease do we explain? Each one of these is a teeny tiny little bitty little signal. This isn't like cranking on that risk wheel way up there or way down there for each one. Little bitty signal, right? No epidemiologist gets excited about a risk factor of 1.16, right? Because you're not explaining personal level risk here. What you are doing, you remember the first thing I said was, hey, we're finding some genetic differences. We're going to learn the underlying biology. We're going to cure a disease, right? That's the story. It's not about saying, Mr. Smith, here's your genotype and I know what you have, or I know what you're going to have. It's not about individual level prediction. So really little bitty signals, and at the bottom end, these are really little, right? These are barely differentiable from the null. They're barely there. And so no wonder it's hard to replicate. They're tiny little signals. Other things to note, and Alice, yeah.
So some of the goals there's not prediction for individual SNPs, but what about when you're going to the polygenic risk scores?
Sure, and so there's a nice paper, I'm not talking about it here, but Vincent Chiraki wrote a really nice paper where we did this. And we will actually talk about, ML will be talking about this tomorrow, or the next day, right? Tomorrow. So I'll just put a footnote on that. It's a great question. She'll answer. Allison showed a nice plot of Sorrel1 being right where the SNP was right over that gene, you remember? So this is a different one. This is the one that's labeled bin1 in your picture. And there's this big, hot spot right here. The SNP looks really close to that hot spot, and everything that looks interesting is on this side. So if I was to bet, I would say, yeah, probably bin1. But could it be regulatory somehow for something going on over here, or over here, or over here, or down here? Absolutely it could. And let's see, so this is from the paper. Genes attributed to a signal were those closest to the most significantly associated SNP. We are aware that these are potentially not the causative genes. So the labels and the causation may not be the same. Whoops, going the wrong way. Here we go. And then I don't know if this is the same one that Allison showed. Might be a different one. But I don't know, right? Which gene? Right? Who knows? I think this one's labeled this, and I think I've seen some PILRA discussion in the literature that PILRA is important. I don't know. But I think it's just important to recognize that when we say this is a gene, that may not mean what you think you mean by a gene. It really means, hey, it's a locus, it's a region of the genome. And this may be, I don't know, this is the endoph or self. Yeah. Yeah, my bad. Sorry. So, yeah, I am getting new glasses. So I had my eye doctor appointment last week. I definitely need a new prescription. So that's my problem here, is it's my vision. Not that it's a confusing signal spread over a large chunk of the genome.
What is the language we're all supposed to use then to differentiate something that is, associated with one gene, right, versus the sort of a marker of a region that has many genes that we have less confidence in what the causal gene or the target gene is?
And
I think we should use the SNP, right? Because until you've actually found the causal variant, you don't know which gene it's contributing to. So to make an inference about the gene itself, yes, you can talk about a locus, because it's a region, it's a region.
But if you try to talk about a paper, you know what I mean? Like, let's say you're trying to talk about a paper, right? And they've already at least annotated that SNP to a particular gene in that locus. Then you just name that gene and follow it with locus, and that's supposed to be how you signify to someone that.
yeah, I think it's like any other concept we address in a paper where there's going to be an operational definition for that paper of what you're talking about. And it may be referred to by an RS number. In this paper, they, clearly in their Manhattan plot, they put labels on. But in the paper, they say, hey, we used the closest gene. And that's what our rule was, and we followed our rule. And we recognize it may well not be causative, right? So I have no problem with that. It's not like the Manhattan plot is wrong because they put in the labels. It would be wrong to take that and say the labels are correct, right? Does that make sense? Well, but people in this room will not do that, right? You've now heard when it says CELF1 that it could be any of these things, and even things upstream and downstream. Yes?
So just to follow Kevin's point, so for those of us who use these kinds of markers in things like polygenic risk scores or Mendelian organization or some of the things I'll touch about tomorrow, understanding or attempting to understand biological pathways are sort of the only way we can make sense of things. And so I think it's very common practice that I'm as guilty as charged to annotate to a gene and then to say, well, we have some kind of suggestive evidence that it's probably doing this, this, and that's why we think it interacts with the social environment in following ways.
Correct.
So I guess what do we do with that?
Well, I think, we're peering through the glass darkly, right? So we're learning what we can with the tools that we have. We're making our best guesses and moving on with the full knowledge that subsequent data may revise our current understandings.
I think if you're doing sort of a pathway analysis or something more complex, the most conservative thing to do is to take every gene under there and say, any one of those. Yes.
Dr. Manley.
You can bookmark this if you want, but just to back up, you tried to summarize why it is we're doing this, because we're looking for potential biological mechanisms or pathways that would increase risk for Alzheimer's disease. That's why we're trying to locate genes. And in Alzheimer's disease or any disease, can you give me some examples where that has actually, where GWAS has led to treatments?
Yeah. So there's a nice story with cholesterol. So one can do a GWAS of cholesterol, and hanging out in the cholesterol GWAS is going to be a gene called HMG-CoA, HMG-CoA. And it's actually HMG-CR, right? CoA reductase. And HMG-CoA reductase inhibitors, they're called statins. Those have had a profound influence on the shape of heart disease in humans in the last 50 years.
So is that the story?
Well, there's a big whole asterisk because it was found by looking at rare familial massive hypercholesterolemia, people whose cholesterol is so high it leaks out of their tendons, right? Which is a really weird condition, but that is actually how it was found from genetic analyses. But it is the case now that a GWAS, of an unbiased GWAS looking everywhere of cholesterol, does find that particular gene, where it could have been the story that we didn't know this about familial hypercholesterolemia, followed through with that, identified that gene, found out what it does, blocked its action, and then we've discovered statins that way. That is not the story. There are people who are seeing today, because of a drug developed from GWAS for age-related macular degeneration. There is a drug. There is a class of drugs for cholesterol that's a new class of drugs that started from GWAS. There are a few examples of success for this many gazillions of dollars of international investment in understanding genetics.
But I think the technology just moved faster than the science.
Yeah.
Right? So 5 years ago, people weren't talking about how do we functionally annotate what this is, and
Yeah.
now people are talking about
Yeah.
it. And it's going to, just because it didn't catch up right away, doesn't
Yeah.
mean it's not going to catch up.
Yep.
Like, we'll be able to identify the genes.
Sir.
The danger is that the funding agencies backed off
Right.
because of the slow movement from
Yeah.
the Manhattan plots and the drug.
Yeah.
When you find your SNP up there, is there like a frame or borders that you can say that, at somewhere in between here? I mean, is there like megabases?
Yeah, and
like that,
I think
plus or minus?
there will be more discussion of these sorts of things with Kyung-Shi's talk, for one. So I'm just going to, maybe, how's that? And move on, because that's, remembering my talk is on phenotyping, so I'm just going to move on a little bit. So this, I think, is from that same IGAP paper, one of the supplemental materials, I think, looks at the population attributable fraction for each of these. And I think this is in the discovery sample, which is always having optimism. So these are too high, where APOE is really important. A quarter of the population attributable fraction is from that gene. The next biggest one here is for BIN1 with 8%. And we can kind of see why in terms of the minor allele frequency and then that odds ratio that I showed you. So that's a fairly common SNP and had a fairly, relatively, for this like really tiny little signals, it was a relatively larger one. Again, going backwards. This is forwards. One of the coolest things about IGAP is, and that's the International Genomics of Alzheimer's project, they made the data available. So all of these effect sizes and p-values and direction of effect at over 7 million directly genotyped. And you've got this, or we talked about putting this on the memory stick, and there's a lot of things one can do with those data. The genetics community is doing this, so this is to be aspired to, where you can make data available for researchers for purposes well beyond what was initially intended. So IGAP was a large sample. There's efforts to genotype way more people. It initially had 1,000 genomes imputation, and you saw from the last talk what that means. And with the HRC imputation, we'll have the possibility of seeing new rare things with big effect sizes, although those may or may not exist, we'll see. It was described as a mega meta-analysis. We have to make up new terms for networks of networks. And the SNPs identified to date are really skewed towards common SNPs with these really relatively small odds ratios. And I think there's an important negative. If there was a common SNP that had even a modest odds ratio, we would have seen it, because it's a really big sample. And it's not yet a huge sample. It will become huge, I'm sure, with the funding initiatives that are ongoing. So a couple of cool extensions to the case control phenotype. So this is so cool. The UK Biobank, so the United Kingdom had a bunch of money and said, hey, we're going to GWAS a boatload of people and study them because the price of GWAS chips has come way, way down. And they only had, of the 500,000 people in their project, they had 55 with Alzheimer's disease. And we've just been talking about you need massive numbers of people for your GWAS. What are you going to do with 55 people? And how on earth are you getting a Nature Genetics paper out of your 55 cases? And the answer is they introduced a new thing called a proxy case control association study, which they termed GWAX. Now, that's just clever. Like, all parts of it are clever. The design is clever, the acronym is clever, and you need a clever acronym writer on your team somewhere, because it's important, because branding matters. It's way too cool. So they have 10.5 million SNPs on 116,000 people, and what they do is they look at, does your family member have Alzheimer's disease? I don't have to wait until you are old to know your family history of Alzheimer's disease. I don't have to go to the expense of phenotyping 116,000 people for Alzheimer's disease. That's real dollars. Anyone who's involved in a prospective study of Alzheimer's disease, that's hundreds of dollars per case to do all of the testing, all blah, 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 and they only have 55. They'd have to wait for decades to have all of these people either convert or not and have useful data from them. But the family history is a single line item in a long interview. And here they are with 20,000 or 30,000 people who have a family history of Alzheimer's disease that they're able to analyze. And this plot is of the IGAP SNPs that I just showed you. This is the odds ratios they found for the family history of Alzheimer's disease plotted against the odds ratios of Alzheimer's disease from the IGAP paper. And they show you, hey, this is the same thing because I'm showing you a pretty much one-to-one relationship between the strength of association at these loci for my family history of Alzheimer's disease against Alzheimer's disease as found by the IGAP study. Non-overlapping samples, so cool. And it's pretty strong evidence that these phenotypes are producing the same thing. So they then do a meta-analysis and combine their data on proxy Alzheimer's disease with IGAP data, and there's new loci that they discover. One of which Joey and I knew about years ago because we did a better analysis, and we'll just not give Joey any more nightmares. So, can we make the Alzheimer's disease phenotype better? If we can refine it, then we can improve our power. So our phenotype, and you've seen something that looked like this before today, where there's a genetic component, there's an environmental component. If we can control for some of that environmental component, if we can regress that E out in any way, we'll have a revised equation where our phenotype with a star, our new phenotype, is a function only of the genetic factor. So anything we can do to limit the E thing makes our G thing shine through. And if you can make your G things shine through, you're in good shape. So there's this guy, Jesse Mez. He's really smart. And where is he? There he is. He had no idea I was going to embarrass him in public. But this is just smart. So what he does is he says, hey, we know some stuff about risk factors for Alzheimer's disease. And I've got these data from African Americans, and I know about these risk factors. What if we put those risk factors into the machine that we use to turn to see if there's genetic associations? And when he doesn't do this, to make a long story and a lot of math short, he didn't find anything at the genome-wide association level of the 5 times 10 to the negative 8th. And when he includes the covariate data, these two loci show up in African Americans. How cool is that? So my summary for the Alzheimer's disease phenotype, IGAP is a really big case-controlled GWAS. It's publicly available. They found 20 common SNPs, each with very modest effect sizes. UK Biobank did a really clever thing with GWAX, and these data are also available. They cost money. I think it's in the thousands of euros, like a couple thousand euros or something for access to that. And given that it's UK, it's probably in pounds now. What's that?
Not to the summary statistics, it doesn't cost money.
So the GWAX data are available?
Yeah, we downloaded them.
Oh, well, there you go.
So the level of data that you can get on that GWAX is the same as IGAP. You don't get primary
Cool.
data
Cool.
from IGAP.
Cool.
You only get the summary stats.
Yes.
Right?
So I guess,
Apply through-
so let me, I did not know this, but I'm going to re-say what Allison just said with my new data, as like I'm updating on the spot. So you can get the summary data, the effect sizes for the Alzheimer's disease phenotype, the proxy phenotype that they had for free right now. If you want individual level data on 117,000 people, so not the summary statistic where you get just an effect size at each SNP, but instead 117,000 data points at each SNP, and through all of the people and all of the SNPs. You can get that with some money. 500,000 people? Yeah, it's a big, big study. It's going to be a major influence on the future of genetic understanding because it's a really big initiative. And then this guy, Jesse Mez, did a really clever thing, taking Alzheimer's disease, controlling for other stuff. And the controlling for other stuff, that is your expertise. You know about these conditions. You are phenotypers. You just didn't think about it that way before. So, yes?
So, Jesse, for your paper, was that
And I'm going to try to answer first. So what he did was, instead of putting the case or control as the dependent variable, he did some math first and threw the result of that math into the machine as the proxy for the case or the control.
So it's basically like upweighting and downweighting individuals based on their probability of having Alzheimer's given their risk factors.
Okay. Okay, cool. And you just did that for...
So it's kind of like looking at the phenotypic, it's kind of looking at the phenotypic extremes.
Yep. So you'd upweight somebody who had Alzheimer's disease who had risk factors that didn't look like they should. And you would downweight someone who did have Alzheimer's disease and had risk factors that looked like they should have Alzheimer's disease.
Yes.
You'd upweight controls who look like they should have Alzheimer's disease but don't.
And you essentially do a regression, get a residual, you have a continuous outcome, and then you use that continuous residual as your outcome, rather than as a case control.
Okay, and we're conceptually at least about halfway through. It's really, in terms of content, about a third of the way through the stuff I'm going to do. And we all doing good? Awesome. So moving beyond. There's sort of two flavors of moving beyond the case control that I think of. One is continuous analogs of the case control. So kind of like case control, only different. And then the other is stuff that's orthogonal to the case control phenotype. And I'm hoping to explain both of these to you in the coming little bit. So another term that you've heard here is endophenotypes. And people have talked about CSF tau, for instance, as an endophenotype, or an imaging thing that looks common among people with Alzheimer's disease as an endophenotype. And this is a concept first used in schizophrenia research, and I read the endophenotype thing on Wikipedia, and I've forgotten now. I think it was some insect I've forgotten. But schizophrenia was the first use in humans. And the idea is that the schizophrenia yes, no, that's really inefficient. You have this whole family and that each person's either a case or a control. Is there anything we can measure that's schizotypal or kind of like schizophrenia where there's gradations? Anything we can do like that will increase our power from the same sample size. And that was the first introduction of this idea into genetics in humans. So are there other quantifiable things that you could examine? And imaging stuff like hippocampal volume, the thickness of the entorhinal cortex, amyloid positivity, things from the CSF, things from cognition with a global cognitive functioning or memory. These are all candidates for endophenotypes, where what you're really wanting to do is discover things that are going to help you to identify genetic loci and cure Alzheimer's disease. But you're not starting with Alzheimer's disease, you're starting with a continuous summary that's kind of like Alzheimer's disease, an endophenotype. So how expensive is your endophenotype? How much data are you going to have for replication? And if you have a uniquely rich data set that's required to produce a fancy phenotype, you just, you spend all your chips at the table, you don't have anything left for replication. And this is a common problem. And it's especially a common problem with ADNI. ADNI is a fabulous data set, very rich. What are you going to do when you find a shining, cool, hey, I might be relevant signal? And that's a problem that ADNI has. And there are additional new studies coming on, and God knows there's funding. So this will be a temporary problem, we hope. And quantitative is a very good idea here. So if you're taking an invasive sample from someone's spinal column where there's a non-zero risk of death from even obtaining the sample and processing it and turning it into a thumbs up or a thumbs down as a total amyloid level, or you're taking a $5,200 at my institution PET scan of their head with the PIB compound, and of course it's now fluorobetapir because carbon isn't stable and fluoride is or whatever, and that's $5,200 at Harborview Medical Center. That's an expensive binary phenotype that you're saying amyloid positive or negative, and if you need 50,000 people for your GWAS of amyloid positivity, You spent a boatload of money if you're using amyloid positivity as your phenotype. So maybe we could do something that's quantitative continuous rather than plus negative. And cheaper, right? So there's some economics of phenotyping that's important. Cognitive phenotypes. So Alzheimer's disease is absolutely something that impacts global cognition. There's no question. Global cognition among people with Alzheimer's disease is worse than people who don't have Alzheimer's disease on average. But there's a lot of other things that affect a global cognitive score. A lot of other things. And that's been the focus of this conference in previous years over and over again. Many, many, many factors influence not just Alzheimer's neuropathology. So there's other neurodegenerative conditions, premorbid intelligence, the familiarity with cognitive tests, education, educational quality, socioeconomic status, and I put in 3 et ceteras. Like a whole lot of stuff that's related to global cognition. It is a mess, and it's hard. So one nice thing about the Alzheimer's community is everybody used the same definition of Alzheimer's disease. The NIN, CDS, ADRDA string of letters that we all have to memorize to do anything in this field, right? Because the McCann paper from '84, it's really an important advance because every study used it to define case or control. Thank goodness. Otherwise, the heterogeneity that characterizes my study and Dan's study and Jennifer's study, all these studies, would carry through to even the what are we labeling these diseases, what criteria did we use, et cetera, and that difficulty with replication would even be there for the case control status. At least that's in common, but that's pretty much where the similarity ceases across these studies. So the way memory is measured in my study and the way memory is measured in Jennifer's study are different. And the way memory is measured in Dan's study is a third way completely. And hell, he designed his own instruments, right? So we know I didn't use those. And he's got some data about how they might relate to the other instruments and so on. But it's a really complicated Tower of Babel kind of situation that requires some work. So some form of harmonization or co-calibration is really important. Or if you're UK Biobank, you just don't care. I'm so big, I'm just going to throw in my test result as my phenotype and run my GWAS, and boom, out pops some stuff. Yeah.
Actually, what I thought was pretty striking, the study that you showed about parental history, was that if you use the clinical criteria, you get the same exact genes and the same exact result.
It's
you ask,
amazing, right?
20-year-olds, which is probably, I don't know if the median age
Yeah.
is young.
It's older than 20, but yeah.
Older than that, but it's still below 18. Right.
The fact that they produced this graph is amazing.
So I think what
This
that
one.
argues to me is that
What the hell are we all doing with all this money?
yes.
Yeah.
Why don't we just ask everybody what their parental history is and never, because we're getting the same results.
I
It's
would say, well, I want to answer this with a personal anecdote. It's that even though I spend my life doing genetics, when people ask me about, would you get your sequence done or your genotyping done, I say, look at your parents and see what diseases your parents had, because that's what's in your destiny. So I think you're right. It's the family history matters. It's what's involved.
You were saying the red and the black line are the same?
no, right? So the correlation is 0.97. They're really, really the same thing that they're measuring.
Well, so maybe the problem is, so you're saying like, okay, you took these people that have genetic history of AD and then you put them as a case instead of as a control, or they put them as a case instead of as a control, and then they saw no difference in the analysis after.
Well, there's more math than that because they were dealing with haplotypes and stuff.
Okay.
And mostly as a respite from the prior talk and because I don't understand it,
Okay.
I didn't give you the math.
Okay.
Right? So there's more to it than what you're saying. But yes, it is remarkable that they got anything reasonable and interesting. And this was one of their example phenotypes in this Nature Genetics paper where they're using this GWAS by proxy idea. It's amazingly useful if you happen to have genotype information on 115,000 individuals. Yes.
Well, so I was going to say, so that's predictive, right? So that's what you're talking about is being able to predict it, right? And you're saying family
Well, that's
history is
usually
so-
what people want to know for genetic data for.
Yeah, but that also means that then there really is a genetic component, and it means that if we are missing all this heritability at the level of trying to identify, right, the mechanism and druggable targets, then the pursuit of understanding what those genes are that are explaining the 30% we know about, right, and figuring out what that other 70% is still totally relevant.
Yeah.
So, like, of course you need to...
I don't think it's a competing strategy. I think it's a complementary strategy. I think that there are some major advantages in terms of the economics of, hey, we'll just do a family history thing in a really big sample. But then some of the questions of, well, what if we limit to people with autopsy, proven, et cetera, there's other things that come in.
I just wanted to add a caveat to this GWAS, which is if you look at the Manhattan plot in the GWAS data only APOE is genome-wide significant in 121,000 people, whatever it is.
Yep.
When you add it to IGAP,
That's right.
you find some novel loci. So there's clearly information in there, and this chart says there's information in there. But on its own, you wouldn't have identified any.
Great points. Great points that I could and should have made. So the effect size at these loci, very similar. And certainly when you plot all of them, the signal looks very similar. None of these reach genome-wide significant with 117,000 people who they GWASed. So you do take a power hit because you're not observing disease status in the individual, and you're getting sort of a half of a person worth of data because you're dealing with their ancestors. And we've spent too much time on the GWAX, and now I'm going backwards again because I'm me.
But we were talking about phenotype Bob.
Yeah, good. Oh, good. So we were talking about cognition. Right. So this is a paper from the CHARGE Consortium, which tried to get through the memory phenotype. And I've forgotten how many people CHARGE has. And they've got a whole lot of data on a whole lot of people. And the studies weren't designed in parallel, so they each made their own choices. But they all measured verbal declarative memory. And this is a really nice figure from that paper that shows the variation across these studies and how verbal declarative memory was measured. So you've got the Wechsler memory scale, the East Boston memory test, the Hopkins, the California, the Ray, a TICS they threw in here as semantically unrelated, like, wow. So, and then here they've got the various different studies listed. There's very little test-specific replication, and they were very careful in this study to only analyze, diamonds with diamonds and clubs with clubs, and not to try to do too much beyond that. The problem is they didn't discover much, right? There was nothing that was related to memory other than APOE in their analyses. And they did some other things to sort of squeeze out a publication, but from the genome-wide association study sort of perspective, this strategy didn't work, despite having data across multiple studies. This is the UK Biobank, where they're saying, hey, we've got our tests of cognitive functions that we gave people. We're just going to plow through because we're big. And so they found some stuff. And they did this really clever thing that's sort of a precursor to talking about gene scores. So they took their GWAS stuff and made a polygenic risk score, and they did it at a bunch of different thresholds. And then they had independent samples, people not in this study, where they had the genetic data and they had some cognitive data from them, and do this heat map kind of thing where these are the four things they had: a memory score, a reactions time, educational attainment, verbal numerical reasoning. Those were the phenotypes that they evaluated, and they made genotype scores for those. And then this is from the Generation Scotland data set, where they looked at these sorts of data. So there was Mill Hill vocabulary score, and they predicted almost 3% of their variability in the Mill-Hill vocabulary score with the educational attainment gene score. So a nice way of saying, hey, we don't know exactly what we're looking at, but this is in an independent sample predicting a phenotype that we care about. This one is the Lothian birth cohort from 1936. What is Lothian?
Lothian.
What is that?
It's an area.
It's an area in where? In Scotland. So I don't know. So clearly, like, what is that? I can't pronounce it. I can't locate it on a map. What can I tell you? I'm a product of Washington State schools. So this is interesting because the sample size of the Lothian birth cohort is about 1,000 people. So now we're getting into the ADNI realm. So part of this big paper is documenting that their stuff is effective in predicting phenotypes in a well-characterized sample. Substitute the word ADNI for Lothian birth cohort, and we're kind of getting into the right size. So we could take a look at their predicted phenotypes with things like hippocampal volume, right? Any sort of imaging-based or CSF biomarker-based phenotype from ADNI would be a feasible thing to do. So we're getting larger and larger studies with better and better data for GWAS of cognition, cognitive-related traits. For people interested in life course epi, educational quality, these may provide important tools that help the epidemiology, help us understand what's going on, and we'll learn more about that tomorrow. And relatively small studies like ADNI could be used in these sorts of ways. And maybe we can predict educational attainment in ADNI and use it as a covariate. So how much education should this person have genetically? How much did they actually have? And maybe both of those are important. Who knows? And maybe use ADNI similar to this Lothian, which I now know how to pronounce, birth cohort. Be orthogonal to the case control phenotype. So we've already visited the IGAP paper. We've done extensions of the IGAP paper with the proxy Alzheimer's disease phenotype and Jesse's cool trick of regressing out what we know about Alzheimer's disease epidemiology and risk factors to get even more power by reducing that E term so that the G shines through. We've done that. We've talked about the idea of an endophenotype or continuous analogs of the Alzheimer's disease phenotype and some cognition examples in particular. So what are other phenotypes that might be useful to look at? And one way to think of this is conceptually as different flavors of Alzheimer's disease. So maybe Alzheimer's disease shouldn't be thought of as one condition, but as many things. And my first example of this is there's a guy named, I think it's Rob Sweet, who has been thinking about this for a long time. And I've seen him at meetings say, hey, if you have data on hallucinations among people with Alzheimer's disease, I absolutely want to talk with you. And so he's postulating that there's two flavors of Alzheimer's disease. There are people who develop delusions and psychosis, and other people who go through their entire course of Alzheimer's disease and never develop that. It hasn't proven to be useful tremendously. This is another paper where they don't really find very much with a pretty modest to intermediate size sample size. But that was the idea behind it, is maybe there's different flavors of Alzheimer's disease. So this isn't, do you have Alzheimer's or not? This is among people with Alzheimer's disease. Some people do differently than other people, and maybe there's a genetic basis for that, and that might be a key to understanding things. So they had 1,300 people with psychosis and 735 without. They didn't have any genome-wide hits, and they did some stuff with schizophrenia-related SNPs. So there's a big international effort to understand the genetics of schizophrenia. There's a big international effort to understand the genetics of fill in your disease of interest here, right? Every disease has people interested in it, and there's papers on pretty much everything that produced that GWAS catalog paper that we saw in the last talk, where across the whole of the genome, every chromosome has lots and lots of different phenotypic associations with it. Anyway, they took the suggestive hits in a replication sample and found that they could predict psychosis. So there's something genetic going on here. It's just not strong enough to be seen with these kinds of sample numbers. So what about contrasts among people who have Alzheimer's disease, we've looked really hard at this with my research group, and we've looked at memory, language, executive functioning, visual spatial functioning, which I call M, E, L, and V, like Melvin, to keep them straight in my head. And we started with data from ACT and then added data from ADNI and Ross and MAP and the University of Pittsburgh. And we've co-calibrated scores, and these are in your data set. And so they're on the same metric. So the ADNI scores for M, E, L, and V are on the same metric as my scores from ACT and from the University of Pittsburgh. And we use these to subgroup people with Alzheimer's disease. And in the most current iteration of these slides, this is where you get psychometrics. So for those of you who thought you were coming to a psychometrics workshop because the name is Friday Harbor Advanced Psychometrics Workshop, please pay close attention. You did see some psychometrics this week. It's not entirely genetics. Here it is. Hold on. So we have an expert committee with Dr. Sakin, who is not here, and Emily Tritschu, who is here, and will wave. I saw her before. There she is. And Dr. Mez. And we've met by phone over the last multiple years to go over these cognitive batteries across these different studies and take a look at each and every single item and assign it to, is it a test of memory, is this a measure of executive functioning or language or visual spatial or something else. Initially we had attention as a domain, and that got axed after we decided we didn't want it anymore. And we did confirmatory factor analysis models using M+. And this is something that Joey introduced us to, which was using clustering to help us understand some of the ways that these items wanted to go together beyond just an overarching measurement of the thing that's in common across all of the items. So not surprisingly, letter fluency and category fluency sort of go together. And take a step back. What are you looking at? This is a cluster analysis, and it's a visualization of a correlation matrix is all this is. The computer sorts the correlation matrix, and it does that in a particular order. So it starts with the single pair of things that is the most highly correlated, and you can see that by how high that little handlebar is, right? So it's the lowest one down. That's the first thing that happened, was this pair of items was really highly correlated. And that's two versions of the Boston naming test that we happen to have in this study. So it makes total sense that those two versions, they're different items, but they're the same concepts administered in this particular study. And then the verbal fluency of animals and whatever this one was were also highly correlated with each other. So those two pairs of items were selected early on. This third pair of recall of objects, A and B, or the naming of two sets of objects within the CASI, I think is what this is from ACT, were highly related. So we had some hints there of things that might be clustering together. We then used what's called a bifactor model that incorporated loadings for all of these items. So we have granular level data from each of these items loading on a common factor here we're calling language because we've assigned it. We can declare this name because I have experts who tell me this is a measure of language. These secondary domains are assigned on the basis of, as it turns out in this case, the computer saying that these things are going with each other. We tried 3 different ways of assigning secondary domains. And it turned out this one had the best fit with the data. And so we use this big mathematical thing, turn our crank, and out pops our language score. So we're getting scores for memory, executive functioning, language, visual, spatial functioning, co-calibrated across all of these data sets using this kind of approach. And it's a really big effort. And the M, E, L, and V scores are in your data set. And what we've done with them, why are we talking about this in a phenotyping talk, and in particular phenotypes that might be orthogonal to the case control phenotype, is we've obtained an average score for each person just by taking the numerical scores and dividing them by 4, and looking at differences between each domain and that average, and looking to see if any of an individual person's domain scores are far below where they should be for that person. It's similar in a lot of ways to the idea of expected and observed. So we expect everybody to have their own individual average level of cognitive functioning for each domain. And some domains are quite a bit lower than what we expect. And we identify those domains. And this is a real person from the ACT study who didn't actually have Alzheimer's disease but was evaluated with the same tests in the same way by the same people. Here are their scores for memory, visual, spatial, language, and executive functioning. They have an average score of negative 0.08. You just take the differences, and those are the differences. And out of this pops this language deficit that's quite substantial. It's quite a lot lower than their average score across the other domains. This person was diagnosed with primary progressive aphasia in the ACT study. So this is a disease that's known. It's usually an early onset disease. There's one of them out of the 1,000 people with incident Alzheimer's disease in the ACT study who has PPA. And this is what happens with their scores. So they have a really intact memory score, which is why they're not being diagnosed with Alzheimer's disease, right? They're being labeled with a different condition. They're being labeled with PPA, and their language score is isolated quite a bit lower than their scores in the other domains. So that's how this system works. Yes, ma'am?
Can you anchor a little bit the scores to those what the
Sure.
expected?
Yep. So the mean and the standard deviation for this metric are set by the people with incident Alzheimer's disease from the ACT study. So prospective cohort study in Seattle, Washington of unselected older people, except that they're members of a healthcare plan. There are 825 of them who had all of my scores, and it's arbitrary, but that's what I'm using as my 0 and my 1.
Yeah, but what does 0.92 mean?
Yeah, so that means that this person had a memory score that was nearly 1 standard deviation above the mean score among people who are newly diagnosed with Alzheimer's disease from this study.
And that's the weighted domain score.
That's the overall M score, the memory score from all of the elements that I didn't show you. This language score, you just saw all of the elements that went into the language score. There's an analogous memory score that I didn't show here. Does that help?
Okay, so that's about the standard deviation below for language.
Yes. Yes.
I'm surprised to see that somebody with PPA would have such intact memory. And because this is actual data that we might work with tomorrow, I want to better understand how their memory score was so high, given that they have a language deficit, and what the tests were, or if it was taking into.
So this is from an ACT participant, not from an ADNI participant, and all of those data would be available to you. Happy to share them with you. Don't have them on my person, but the data are available. And this isn't how we had intended to use this, right? So we intended this just for people with an Alzheimer's disease diagnosis, and did this for this particular person who came in with this sort of positive label already attached to them. Yeah.
And it's not that this person had memory that is better than all the people in their age range. It's that it's compared to the Alzheimer's. It's going to be to keep that comparison in mind the whole time, because otherwise, as neuropsychologists,
that's a great point.
you start to think, wait a minute, that makes no sense.
This doesn't mean great memory. This means better memory than average among people who are newly diagnosed with Alzheimer's disease. That's a great point, Emily. Thank you. So this person has primary progressive aphasia. And I don't know if this helps, but here you have 4 escalators going down, right? And Google is amazing. And I've got 4 symbols of where this person's cognitive functions are. They've got an average cognitive functioning that looks like that. And that square is quite a bit below that person's individual average. So my point here in a phenotyping talk is the absolute position of this plus or this square, I think, is not a very good phenotype, because this is a disease that evolves over time. Everything is going down over time. And I've given you this very suggestive thing that they're all going down perhaps at the same rate. Otherwise, it's a very confusing looking escalator. If you could imagine a moving picture with different rates of decline for different cognitive functions, which is quite possible. But at least by taking an average and a difference of an average, I'm getting something a little more stable, perhaps, than the level of this square or this circle at any particular time. This square used to be higher for this person. That's not a good phenotype of something that's changing over time. I suspect that the relationship of the square to the individual average is more stable over time and thus a better phenotype. And I'll show you some data that I think it is a pretty good phenotype. So we've applied this framework to people with undifferentiated typical Alzheimer's disease in ACT with a paper that is out now in Alzheimer's and Dementia. And what we found was that the people with isolated substantial memory impairment had higher proportions with APOE. And this turns out to be consistent in the literature. I had steadfastly ignored APOE papers my entire career, and then I had this result. I'm like, wow, I better read these. And it's commonly found that APOE4, among people with Alzheimer's disease, they have more memory problems than people who don't have APOE4, that their memory impairment is more substantial, is a common finding. And the most fascinating paper was from Mexico City, where there was not an association between APOE4 and Alzheimer's disease risk. But in that population, if you had APOE4 and you had Alzheimer's disease, your memory was worse than people who didn't have E4 who had Alzheimer's disease, suggesting perhaps that E4 might have two different roles. One is to increase your overall risk of having Alzheimer's disease, and then given that you have Alzheimer's disease, having a unique effect on memory in the hippocampus, and there's a whole lot of literature that suggests that might be true.
Or it could increase your risk of being diagnosed with Alzheimer's disease.
Sure. What we found was age at onset was pretty consistent across all these groups and was not related to either E4 or the memory group. And we found that this group with isolated memory impairment had a higher proportion with Braak stage at least 4, higher proportion with cerebral amyloid angiopathy. They looked like a sort of a group that had more AD-like features as 18% of all people with Alzheimer's disease. Our proportions in the ACT study are not what we find in all of these studies. So here's ADNI. ADNI has an awful lot of people who have no domain that's sticking out a lot and saying, hey, I'm different, but not as many as ACT had, and a whole lot more people with isolated substantial memory impairment than in the ACT study, and similar proportions of people with a language impairment, similar proportions of people with a visuospatial impairment. Multiple domains is common, relatively common in both. So, and I think there's important things with ADNI and Pittsburgh being both research studies, convenience samples, clinic-based samples, and ACT, ROS, and MAP being prospective cohort studies. There's a lot going on here. But the flavor of Alzheimer's disease that experts see in their study is not reflected by the flavors of Alzheimer's disease in other studies, which is what this says. If there's different implications for these different groups, it might be really hard to replicate things. And what experts think of as typical late-onset Alzheimer's disease may vary based on their own individual cohorts' makeup of what is Alzheimer's disease in my study. So I told you that in ACT we found that the proportion of people with E4 was higher than everybody else. And here we have consistent replication across 5 studies. This dark purple color is at least a 10% difference from the overall average in that study. Here is my p-value of 10 to the negative 26, comparing the E4 positivity in the group with isolated substantial memory impairment to the other groups, where it's 46% across all these studies. So this 51% includes this group. Right? When you remove this group, everybody else has 46% E4 versus 65% E4 in the isolated memory group. And this just fills in the rest of that table and shows you the profound difference in E4 positivity across these different groups. 5-fold replication across studies of this finding. And we're coming back to my favorite IGAP SNPs. We'll beat them into your head, right? You can memorize them all. No, we were not going to do that. But what we show you here, I've selected these stories because they're really interesting. So here's the firm T2, where in the Lambert paper, the odds ratio is 1.14 for the firm T2 SNP, right? So it's not firm T2, but the one that's labeled firm T2, same RS number, same everything. in this group who have relative memory impairment, isolated substantial memory impairment, the group with the higher E4 positivity, these are my results from ADNI ROS map that I put together for numbers that Joey put together because he did all the work. And here's the ACTS and the Pittsburgh answer. So in each of these, the strength of association is higher in this one group than it is overall among people with Alzheimer's disease. And for these 3 SNPs, that is true. For relative visual spatial impairment, for these 2 SNPs, it's driven by this group with visual spatial impairment. And I was amazed that there was anybody with the multiple domains group. Like, this could be any 2 domains. It could be memory and executive. It could be language and memory. It could be visual spatial. You get the idea. It could be any pair of domains that's really sticking out and saying I'm impressive. And it does vary quite a bit. And yet there's genetic similarities driven by this group for these 3 SNPs, which is really interesting. And we left ACT out because there were only 12 people with ACT. That's actually how we set how far is our threshold for really big, was by trying to minimize the number of people with multiple domains in the ACT study. So that set our threshold for this is a really big difference. And there's only 12 of them, so they're not enough to meta-analyze. And yet, look at this. Those are the data for those 3 SNPs in the ACT study who are left out of these. They're even more impressive for these 12 people in the ACT study. So very consistent study-to-study replication of stronger signals at IGAP SNPs for these groups. And this is showing now for FIRM-T2. I showed you the memory result before, where it was stronger for the memory group. This is showing you pretty much the same as among everybody for the people who have no prominent domain, and pretty much null for everybody else. And those ones I've got listed on here, and they're colored purple over here. These are driven by just one of the subgroups. And in contrast, there are these ones. This was green on my screen. What is that? Tan? Mustard. I like it. Like a good quality mustard, too. This isn't the neon yellow mustard. So this one for ABCA7, it's pretty consistent across all my subgroups. So there's some IGAP SNPs that are driven by one subgroup, some that don't tell much of a story at all, like the sorrel one. I couldn't make up a story because it's all over the map, and some that are some that are pretty equivalent across all of them. So all IGAP SNPs are not created equal. If there are subsets, yes. Yes.
If you look at the 95% confidence intervals around the results ratios, do they all overlap still with the data from IGAP, or are they actually significantly different from the IGAP?
Joey, is that a no, we don't know yet, or? We haven't looked. I would be surprised if the 95% confidence intervals overlapped.
Really?
Yeah.
I wouldn't be surprised at all, because your sample is so much smaller.
Yeah, but certainly the 95% confidence interval around this with 74,000 people is very small indeed.
Yeah, but your confidence interval is going to be huge.
I don't know. Well, sure. So, newish data, smallish samples. It's never been looked at before. Like, well, who knows, right? So in the fullness of time, we're adding more data sets, and we'll be narrowing them down. And who knows, right? I'm showing you 5 studies worth of replication. Study number 6 could absolutely be in the opposite direction or whatever, right? So bad things happen on the way to the big journal publication.
Hey, Frog, while we're paused, can I ask a question?
Sure.
Keep using this word SNP, and you've got genes labeled on the slide.
Yep.
I thought I learned this morning that we weren't going to label genes when we're talking about SNPs.
Yeah, and you heard Dr. Crane say, I have no problem with people calling these by this thing, with the caveat that they're using them in the same context in which that thing was labeled. So when I say a gene for all of these things, and I'm getting ahead of myself, all of these, this really means the tag SNP. And Joey was very careful to make sure he was looking at exactly the right RS number. Each SNP, and we didn't say this out loud before, each SNP has a unique RS number. I don't know what that stands for. Reference sequence number, maybe? Anyway, it's a unique identifier for each SNP. So these PTK2B is not just anything in that loci, in that gene. It's the particular thing that was labeled as PTK2B. Absolutely. This should not say gene, it should be say tag SNP. If that's fine. Okay? Tag SNP means the SNP that was identified, that's tagged. Okay? It's a good question.
Okay, so I have a question.
Ah. Yes.
So, we did something really similar with the Women's Health Initiative memory study data. And not just with the GWAS SNPs, but looking at candidates we had identified in the mouse by looking at different cognitive domains. But one of the things that we realized in that data set is that the covariates, like hypertension and other things that normally get regressed out evenly across the cohort when you're using a composite, affect cognitive domains differently. So when you're, did you first go through and look at whether or not your covariates are contributing stronger to variation in each one of those domains before you regress them out?
Sure. So we've got good data from ACT from one study where we've looked and what we've found is nothing. We haven't really found any relationship between age, education, age at onset, calendar year, sex. I've forgotten what else we've looked at. I've got a couple of undergraduates who have worked closely with Laura to look at risk factor profiles. There was a depression score, I think, that came out for one of them, but that didn't replicate in Rosten map. So, don't know. This is a tool where, and I think this is sort of my key point here, is that these groups are ignored in the literature that's working on the genetics of Alzheimer's disease. And I don't know that I can prove to you that there's a biological relevance here. I think there is a biological coherence here, and it's not unique to our group to look for subgroups of people with Alzheimer's disease. We have this framework for doing it. You don't have to buy it necessarily. I'm certainly going to be turning this crank for the next several years in my lab. Allison?
I'm curious whether you've calculated an IGAP polygenic risk score. And that's difficult in these data sets because they are subgroups of IGAP. But it might be interesting to know, based on your phenotype, how that polygenic risk score varies. And whether you could actually demonstrate, even if you're not looking at individual loci, that overall there's less AD risk in these different phenotypes.
It wouldn't shock me if Joey just wrote that down as a thing to do.
We talked in the morning about
Coming soon.
Okay.
And you'll see some data in a few minutes that I think are interesting along the lines of these are a subset of people with Alzheimer's disease in the IGAP study. So I flipped on this a few times. So this is a heat map again, but now we're looking at the odds ratios from that table I just showed with the green and purple coding, mustard color and purple coding. And so the very last things is what I focus on here. The very last thing to happen here was that these three SNPs got put together with all the other SNPs. And you see that by, I'm going to flip to this one because I can reach it. I'm only so tall because of my genes. This one here is the very last thing that happened. And as we move right, because this is a mirror image at a 45-degree angle. So the second to last thing was that this group of SNPs and this group of SNPs were combined together. So the whole thing is sort of three clusters, if you think of that. And this was agglomerative. Is that right, Joey? Oh, nice. So I'm learning new stuff. Clusters, right? So those are the way that the computer says these odds ratios are put together. No one's had those odds ratios before because no one's carved up people with Alzheimer's disease like this. And this is taking the whole thing, and this isn't just the ones that are the stories that Paul thought were the coolest to illustrate with purple font. And so those are the three clusters that are there, and you can kind of see like this pretty distinct difference in color between this little island, and this little island, right, with a little bit of blurring stuff going on over here and here. Yeah.
What is in blue and what is in red?
Yeah, so this is strength of association, positive and negative. Yeah.
But it's not the odds ratio, protective versus...
Those were the underlying data that went in, was the odds ratios.
And you have the asterisks to tell us that the ones that were protected.
Correct.
Okay, yeah.
So very intriguingly, when we label these with my annotation of visual, spatial, and multiple domain and memory, and I threw APOE in here as a memory SNP with its 10 to the negative 26 or whatever that was. So this is the memory and some that were equal across. This is multiple domains with some that were equal across. And this is visual, spatial. So very intriguing. This is an interesting paper from Schott and colleagues on posterior cortical atrophy. So this is a rare Alzheimer's disease subtype commonly found in young, early onset Alzheimer's disease. They don't come in complaining of memory problems. They complain that they cannot see. And their eye doctor looks at them and says, there's nothing wrong with your eyes. Or there is something, here's a new pair of glasses. And they get their new pair of glasses and they say, I still cannot see. And they come back and eventually someone says, you need a neuro-ophthalmologist. And the diagnosis of posterior cortical atrophy is made. And if such a person dies and comes to autopsy, they have plaques and tangles, but it's not in the typical Alzheimer's disease distribution. And it's thought of as a Alzheimer's disease subtype. So this is a group that was spurred on by the rare Alzheimer's subtypes professional, interest associations, the PIAs, in the AAIC, Alzheimer's Association International Conference, because branding is important, right? So this group pulled together resources across the world, 302 people, which is an enormous study for this rare condition. And they had, their biggest sample was from the group at University College London, and they go down to some centers that contributed a total of 6 people each. So lots of centers, very few participants per center. And they looked at the strength of association of 19 of the 20 IGAP SNPs. So these IGAP SNPs keep coming back because everybody knows these are mileposts. These are guide markers to what's going on in Alzheimer's disease. And this is the same as the GWAX papers approach, where what I'm doing is looking at my group with isolated substantial visual spatial impairment compared to this group with posterior cortical atrophy at IGAP SNPs. So this is a subset of people with Alzheimer's disease, and I'm looking at their association with a different condition by looking at the strength of association at the IGAP SNPs. And what we find is that the strength of association with the beta coefficient being higher with the PCA SNPs than with the Alzheimer's disease SNPs. The R squared is higher for the PCA SNPs. The correlation coefficient is higher. This is more like posterior cortical atrophy than it is like Alzheimer's disease. At IGAP SNPs, even though all of the people I'm studying are in the IGAP analyses. They are IGAP cases. This is ADNI and ACT, and this is Ross and MAP. And the University of Pittsburgh, all of those are in the IGAP sample. So this is a subset of people with Alzheimer's disease who are really looking like they have a different condition. So IGAP SNPs driven by the visual spatial group do not seem to cluster with the other SNPs. This visual spatial group has a stronger association with PCA than it does with AD. And this is the point I was just making. They're included in the IGAP case control phenotype. I would argue they have something that's at least AD with an asterisk, very different looking. And this successful subgrouping strategy may provide a tool to further our understanding the mechanism underlying distinct subgroups, and it may point to new directions for research and therapeutic development. The phrase that pays, right? So we use these same data sets. We, again, means Joey. Use these same data sets to perform GWAS. And now the case is my membership in a subdomain. And we have really small samples. This was stupid to do, right? Too stupid. But I showed Joey the shot paper on PCA, and I said, hey, they got a nice publication with 302 people. And that's pretty similar to our sample size. Let's see what we can do. And we might see something, even with these ridiculously small groups, because each one is a cleaner phenotype. It's the phenotype. And this is our finding for the visuospatial group, where we have a genome-wide significant SNP here on chromosome 6 with a nice broad area of chromosome 6 that I'm not going to show you here. And the tag SNP has an odds ratio of 2. There was no odds ratio of 2 in IGAP. Why? Because this is a cleaner subset of people who have a thing that is more like the other people with that thing. And there is a genetic association that's very strong in that group that you cannot see when you add everybody else who has some other flavor of Alzheimer's disease. All of that noise and randomness overwhelms this really strong signal from this group that's genome-wide significant with a sample size of 310 people. So it's a cleaner phenotype. It's the phenotypes that's going to be the next generation of cool stuff with genetics.
Is that HLA?
It's not HLA. We'll talk about that. We'll talk about what it is later, maybe. This is APOE. Okay? And I thought, I didn't show here, the APOE signal is massive for the group with isolated substantial memory impairment. And it's also there for all the other ones. And I was thinking, it'll be in a different direction. But no, APOE4 is a risk factor for all flavors of Alzheimer's disease. It's just an especially strong risk factor for isolated substantial memory impairment. And I was like, well, is the direction different? No, it's absolutely a risk factor for being in this group too. And so we've truncated this at some reasonable level so you can see what's going on here. If you just let the computer plot it, it makes a really big spike for APOE, and this line is shrunk down to about here. You can't tell what's going on.
This is 310 cases plus 1,200 controls.
Correct.
Yeah.
So somehow we went backwards, I think. And that's because I'm holding this upside down. I diagnosed my problem, and I treated my problem. The multiple domains group, this is just one of the other domains where, again, APOE is sticking up. And even though this is a very heterogeneous group, even though it's only 200 people, I've got these 2 thought control marks here of, wow, those look like pretty interesting loci. We'll have to need more data before we say much definitive, et cetera, et cetera. But pretty exciting that there's looking like stuff going on with only a few hundred people, but a cleaner phenotype. So cleaner phenotypes lead to much greater power. We've got this novel locus on chromosome 6 with an odds ratio greater than 2 for one of these subsets. And there's many more loci poised to become significant with more data. Thor is hungry. Thor is the name of Joey's computer. And Thor needs more data. Yes?
One more detailed question. I'm sorry. The PCA phenotype that you had in your low group, were they younger than the rest?
No. All of these people are late onset Alzheimer's disease, and no difference within the ACT study. And I did look at the other studies too. There was no difference in age. And in the ACT study, this is in their 80s on average, is when we diagnose people with Alzheimer's disease. And there's variation, but there's no systematic relationship between age in any of these 5 data sets and any of these subgroups.
No, but in the subgroups, like in the visuospatial predominant, they're not younger.
They're not younger. Same. So, going back to our big, that's all I wanted to say about my cool Melvin story. So, broad category 2 still is other phenotypes that might be orthogonal. So resilience is a really cool thing. And this is the very last chunk. You're almost there. You're doing a great job. And, kudos to you because it's a long day. It's a lot. It's a lot. So the genetic architecture of resilience of executive function, this really cool guy, Joey Mukherjee from Seattle, led this. And this is a Friday Harbor 2011 paper. How cool is that? So this was our work group. And we quickly said, like in a minute and a half in our work group, what's our phenotype? Well, let's do resilience. Resilience of what? And it was like, wow. There was suddenly agreement that this was a cool phenotype. So there's a lot of things that are associated with executive functioning, including age, education, atrophy, lacunes, white matter hyperintensities. We used a regression model to predict what should the expected executive functioning level be for this person. And then we looked at standardized residuals of that. So the executive functioning beyond that predicted by the independent variables. And if you excuse the analogy, so there's people who have Swiss cheese for brains, right? They've got terrible looking brains. And they have all the wrong executive functioning risk factors, but they have a great executive functioning score. I want to be that person. I want to take the drugs that give me a phenotype that looks like that, right? This person's got Teflon brain, right? It doesn't matter that they've got Swiss cheese for brains. They're doing great with their executive functioning, right? So that's one end of the extreme. The other end of the extreme, by the way, is me before my coffee, right? I'm having a really bad day. My executive functioning is worse than predicted by my covariates. My brain looks great, but my executive functioning is terrible. I might be really depressed. I might have woke up on the wrong side of the bed, didn't have my caffeine, whatever else. That's at the other end of the spectrum. And way deep in the paper, we did some analyses to find out if our interesting genetic signals were from which end of that spectrum. And sure enough, it was the resilient end that was driving things. But at least in theory, it could be the other end. I would argue that not having caffeine yet in a day isn't going to be a genetic factor, whereas having a Teflon brain may be genetically related. And fortunately, that wasn't wrong with the data.
Was it cross-sectional yet?
Yeah. This was cross-sectional, this phenotype. And what else did we say here? I'm going backwards and forwards. So it's an important thing to think about in Alzheimer's disease of, is my goal to be an AD endophenotype, or is it to be something that's orthogonal to Alzheimer's disease? And if you're incorporating data across all of ADNI, you need to be very clear with yourself about what am I doing here. So this is a graph from that paper where the top one shows you kernel density plots of executive functioning across people who have, let's see, the blue is people with normal cognition, the red is people with MCI, and the green is people with Alzheimer's disease. Not surprisingly, there's a strong relationship between which of those groups you're in and your executive functioning score. There is still heterogeneity, so some people with normal cognition, where is my ruler? Oh, now I have power. Right? So some people in this blue group have scores that are lower than some of the people even who have dementia happen to have pretty good executive functioning. Some of these people with MCI are at this extreme, some at this extreme. So there's heterogeneity within the groups, but you can see there's definitely a central tendency that marches out the way you'd expect. Right? So if you just throw executive functioning into your GWAS, you're going to get Alzheimer's disease out, at least as part of it. So when we then looked at our residuals, we helped with that quite a bit. So the blue one is still people with normal, people with MCI, people with dementia. It's kind of pushed towards the middle, but not enough. So the other thing we did then was we threw in a memory score. And when we also controlled for memory, now our groups are really superimposed across each other. So memory is acting as our Alzheimer's disease stage surrogate. And so that gives us a phenotype that's well matched across the groups. If you are going to do something fancy with Alzheimer's disease related phenotypes and want to do something orthogonal, this approach of graphing your thing across different groups in ADNI, I highly recommend as a means of testing, am I just rediscovering APOE because it's Alzheimer's disease all over again, or am I doing something else? Did that make sense to people? Late in the day, glazed looks. Yeah? Other people have certainly looked at the idea about residuals. So White and colleagues in this year have a residual cognition. They're using a global cognition, which is a big Z-score, and this is Ross map, I think, adjusting for a bunch of different things. It's the same idea. And this really smart guy, Tim Homan. Where's Tim? There he is. Great paper, right? So he looks at resilience to amyloid. So he then had a regression model and predicted this really cool paper on Crane et al. ADNI MEM, it's great. And Gibbons, where's Gibbons? There she is, right? The executive functioning score, he regressed those things. And it's really cool because we put these scores back in the ADNI data set, and anyone can use them for any purpose, including crazy things like, no, great things like this, where he regressed out what should the cognitive decline be doing and how much more can we explain and so on with the genetics. So I've already told you all of this stuff, that Alzheimer's is one of many things influencing cognitive scores. There's many other things, and we can clean up the mess a little bit. That residual might be really interesting and important as a really interesting phenotype that teaches us something about the biology of human brains and how they're able to react to disease processes that you can see with neuroimaging. And that's a really important phenotype that may help. I could imagine taking my resilience pill separately from my Alzheimer's disease prevention pill, and that those might be two completely distinct sets of biology where both might be relevant, and the two in combination might give me the best chance to avoid this really awful disease and its effects, right? So maybe you get the Teflon brain where the disease is just ravaging your brain, and phenotypically you're fine because you're resilient. So these were my objectives where we've looked at the Alzheimer's disease case control phenotype, some cool extensions with the GWAX idea and the regression idea of Dr. Mez to try to oomph a little bit more by taking what we know about epidemiology and applying it in a genetics setting. And then moving beyond the case control, where we've talked about phenotypes that are continuous analogs of disease state with endophenotypes, and then phenotypes that are orthogonal to that with subtypes is one category, with the delusions among people with Alzheimer's disease, and then my crazy Melvin idea, and then the resilience idea as another thing. So there are tremendous opportunities, I believe, to apply our clinical intuition and our understanding to further the scientific understanding of underlying mechanisms about late life brain outcomes. And the cleaner the phenotype, the stronger the genetic signals. And I hope I've demonstrated that even with a very small subgroup of people, if I process them in such a way that they're more like each other than they are like other people among people with Alzheimer's disease, that signal can shine through even with a relatively smallish sample. Or, in a nutshell, it's the phenotype stupid. So there's tons of people who've worked on all of this, and Joey has done a tremendous amount. I'm going to hate this because I'm going to embarrass him now. He's not a very public person. He would rather be just in the background, but he does a tremendous amount of work. And my team with Laura and Elizabeth and so on, who's back at the office, along with Elizabeth, have done a tremendous amount of work on this project and on this week to make Friday Harbor work so well this year. So I'm really lucky to be the spokesperson for this large and creative and awesome group of people. So thank you so much for your attention. If there's other questions, we could take a few now, or we could just call the code and just stop, and I'll be around all week.